It's my pleasure to introduce Rafał Kocielnik, who is an accomplished postdoc at Caltech. His work is cross-disciplinary. He's currently collaborating with Cedars-Sinai and Activision, which is a gaming company. So he has a wide diversity of interests, and I guess you could say that his research focuses on the intersection of AI and human-computer interaction. So yeah, the floor is yours.
Thank you so much. So yeah. Yeah, thank you so much. And right. So my name is Rafał, as I've been introduced. I'm a postdoctoral researcher at Caltech currently, but I completed my PhD in human-centered design engineering at University of Washington. And today I'm excited to share with you my work on kind of human AI interaction projects. And specifically, I want to talk a bit about how important human AI interaction is in different applications. And I will showcase some applications in very specialized things on surgical training, but also how important it is to support it for inspecting, understanding the capabilities and challenges of AI systems. So, but before that, I would like to thank everyone for giving me the opportunity to present here, and everyone who is attended for your interest. So, just a quick overview of kind of my interdisciplinary research journey. I'm originally from Europe. I started my work in research back in Europe, and I worked on kind of computer science and industrial design projects. Especially, I work on technology already kind of related to users in effective computing. So and around stress and burnout using wearable sensors. And at that point, there was very much technology that affects people. I got really interested on the kind of human side of the equation and diving deeper into how can we support users on the human side, and that motivated me to start a PhD at University of Washington in Human and Engineering department, when I really worked on kind of user-centered design projects. My thesis was on creating engaging conversational AI systems for behavior change along health and productivity, and I learned a lot of things on the kind of user side. And after that, with the latest advances in generative AI, I was interested how can I join this college, apply some of the modern deep learning techniques, and that drove me to apply for a computing innovation fellowship, and I joined Caltech as a postdoc, where I work on some of the specialized areas like clinical support systems, but also kind of explainable AI tools. So with this, I want to talk to you about the two big areas of my work, and I will showcase specific projects in this area. So one is AI for health and productivity, and the other one is end user inspection of AI systems. And let me start with the AI for health and productivity. So in this area, I've done work in different topics. One big topic was conversational AI in health, where I worked on using conversational AI systems to promote physical activity, to also help screen patients in hospitals, in emergency room for social needs. I have a big area on workplace productivity when we use conversational agents to support scheduling and support reporting at work, as well as to support qualitative analysis. But in this talk, I will specifically dive into a project that I've done at Caltech, which is especially on the AI in health and clinical area, on helping with surgeon training. So with this, the project I can talk about is about using deep multimodal fusion for surgical feedback classification. And what is surgical feedback? I will actually introduce in a moment. But this is a collaboration done between AI experts at Caltech and NVIDIA, but very much with involvement of practitioners and actual surgeons from Cedars-Sinai, also USC Keck Medicine. So to give you a context of the work, the robot-assisted surgery, which is the context of this project, involves essentially a surgeon operating a console, as you can see here. And this console, like the surgeon can remotely control the robot that you can see behind. And these are essentially this kind of teleoperated surgery. And the surgeon, what the surgeon sees is actually the camera feed from the arm attached to the robot, and can see a zoomed-in version of what they operate on. And there could be other people in the room, and there's actually a more complex interaction in the operating room taking place during the surgery. Specifically.
So wait, this is something that happens today?
Yes, there's something that happens today, but it's remotely controlled. There's no robot automatically doing surgery.
No, I understand. Yeah. And also, how long do these surgeries last typically?
It depends on the type of surgeries. The types of surgeries we worked with, there's like, it's in urology. So they're like 2-3 hours, sometimes 4 hours. That's usually the length. Yeah. Yeah, so the context here is essentially, these of course are already specialized surgeons. They know they're allowed to perform surgeries on patients, but there's still an important kind of, in some ways, less stage of training going on when you have a more experienced senior surgeon giving feedback and guidance to a less experienced surgeon, but still at the, already they have experience to do surgeries. But the guidance is in a form of essentially a verbal feedback, telling, be careful with using your energy near the artery, or pointing at something, some anatomic component, and saying, watch out not to do incision there, or deal with this bleeding, or things like this. And that's the kind of the context of the training that happens in a kind of informal way in the operating room. And why is this important? So there's not that much understood about this aspect of training. There are earlier stages of training that are a bit more formalized, but this is actually important in the sense that there is indication showing that the way the senior surgeon gives feedback affects the training process, and affects not only the correction of immediate surgeon does, but also the acquisition of skills in the long term. So how well do they train how to perform surgeries? The challenges here are actually that this is, it's hard to obtain data. It's very specialized data sets, but also it's not necessarily clear how to categorize or understand what are the important aspects of feedback that really affect whether the trainee learns better or not. So what we did in this project, we tried to look at how can we define meaningful categories, meaningful properties of feedback, and then how can we automate kind of extraction of the categories from this multimodal data. As I said, there is a video, and there's the audio happening, and the verbal, non-verbal communication. So in the end, what we want to achieve, like from the user perspective side, one thing that this capability enables is, for example, providing kind of potentially a dashboard for a trainer, when you can quantify the properties of the feedback that was given in this operating room, and it can help the surgeon look at what kind of things they had to give feedback on, what were the moments when they had to give feedback, and then what was the reaction of the trainee. So it's kind of a longer term, one of the avenues that this work can really help with. So yeah, so the contributions, before I dive into the details of it, first of all, there's the novelty here in the sense that I think we are one of the first to provide kind of clinically validated classification system for this kind of informal feedback. We are also one of the first to automate it to some extent. There is some of the technical innovation part when we also looked at introducing kind of stage training for fusing modalities, whereas a lot of prior work looked at different model architectures. So we show it in this context. And finally, the broader impact is, of course, as I mentioned, the feedback dashboard that this capabilities enable, but also ability to inform targeted studies when you can see what is happening in the real world, you can quantify it, and you can design a specialized study to see what you can compare, what is more effective, and of course, down the line, real-time coaching can suggest contextual feedback. So with this, let me tell you a bit about the categorization system that we have developed with clinicians, and this was our earlier work, when we basically looked at what is a meaningful way to categorize the information that is being delivered in the feedback. It's clinically meaningful, what are the categories that are distinct and informative. And the categorization we came up with is into the feedback being anatomic, so pertaining to anatomic components and guidance on the landmarks and anatomic structures, the feedback about procedures, so versus the timing and sequences of surgical steps, and in which way they are executed, what should be the next step. There's the technical feedback, so it's less about the timing and the sequence, but how well you execute particular steps. So how do you use instruments? And there are additional components like praise, whether the trainees are being guided, and also enforcement on whether they're doing correctly something or not, and it's clear. And visual aid, which is also in this multimodal context, assisting the trainee to understand what they should focus on with kind of pointing at things in the visual field. So one thing that is important is that these are not mutually exclusive. The feedback could be about anatomic things, they could relate to technical part at the same time. And this is just to show you, these categories are actually not arbitrary. They were developed with clinicians, but also we have shown with analysis from a biostatistician that they're actually predictive of some of the important behavioral factors. So the praise, for example, how frequently the praise is given depends on the experience of the trainee and can significantly differentiate less and more experienced trainees. That the technical and visual aid, we have shown that the visual aid is, in addition to technical feedback, so the technical feedback delivered with visual guidance is more effective at changing the trainee behavior than just the technical feedback alone. And similarly for anatomic feedback with additional reinforcement for basically a positive feedback, right? Reinforcement and praise is also more effective at changing behavior. Now, okay.
Wait, I have a question.
Yes.
What about, did you look at negative, kind of like yellow anger, like some sort of negative?
We looked at negative things and they are there, but the finish is it's really rare that the surgeon is explicitly negative. It's more like you will have a praise or you would have like just guidance without the praise, which essentially means that, that there's something to improve. But it's very rare that you have explicitly
Maybe
negative.
it could be, well, it's kind of surprising, but could it be the observation effect, kind of whatever that knowing that they're being observed that might change their behavior?
That's an interesting question. I mean, the way we collected this data, it's in collaboration with the surgeons. So they basically, they recorded in this way. You cannot rule that 100% out because of course, you have to consent to it, right? And you're aware, and the surgeons are aware that this is being recorded. So there is a possibility like that. Yeah.
Yes, and sorry if I missed this, but then just in terms of how you developed these categories,
right.
Did you bring in clinician validation of these categories after you had done your, applied your various methods to identify the patterns?
Yeah. So that was actually, yeah. So there are two parts to this work. One is this categorization, which I was kind of a co-author of, but I wasn't the main author on this. But that was, in a way, that was purely manually done. They were looking at feedback, coding it, and creating the data set, and then coming up with, a coding scheme.
Okay.
And then this coding scheme we validated in a way that it's meaningful. And the problem with this coding scheme that it still requires, like, if you have new surgery, you have to bring in and you have to code everything manually, and you cannot have a novice code it because it's very specialized, right? So you need to know what it means to deliver anatomic field, what it means that something is technical, and how to categorize it. So the second part of the work that I'm going to talk about is kind of automating this part as well.
Okay.
But the assumption is it was validated. It's published work on media, which is like a good venue as well, and it was we have checked it in terms of it wasn't developed with a view of changing behavior, but it has been shown that it actually correlates with the changes in behavior.
Okay, but like just it was done more manually, and by it was done through expert.
This part was done manually, yes, through effort of like developing a coding system and basically qualitative analysis.
Okay.
Okay, so yeah, so a warning here. I will show, like, to give you context, I will show some of the actual real footage from the surgery, and it's kind of zoomed in because it's from a laparoscopic camera, but it still could be graphics. So I just letting you know. Okay, so yeah, so I talked about this feedback, but to give you a really concrete example how it looks like, I can give you a short video.
And the dexterity of these robots is perfectly adequate, huh?
Yeah, sorry, it didn't play the audio. But anyways, what is being said is that, just stay in the yeah, there was audio. I thought the audio would play. Sorry, the dexterity of the
those robots have really fine dexterity for.
Yeah, so I actually use the robot just for a practice task. It's you have a lot of control, but there are interesting things. I'm not gonna dive into this, but okay, I'll share a bit.
So there are constraints.
There are constraints in the sense that you don't have a really good haptic feedback. You have, there's a mapping between how much movement you do in the console, how much movement happens there, obviously, because you have zoomed in things. So there are many ways, like for example, you have a pedal and you press, so you can detach the control from this. So you can, for example, you can move further in the physical space that you could, what you have on your console. So there's some learning curve on mapping. It's not, it requires some practice. And we've done studies before with like pure novices and kind of errors they do. And some people are innate. And I'm not going to dive into it, but there's published work as we have shown into kind of reducing errors for novices training this. And there are people that are innately good at this. So they start in, they're pretty good. But there are people that struggle more, but there's a learning curve.
My knowledge of this comes from a TV show called The Resident.
Yeah.
My knowledge of this comes from a TV show called The Resident, and there are basically doctors who kind of struggle with it. Yeah. Doctors who are used to conventional surgery kind of find it hard to go through this learning of operating robots. True, or is it easy to?
Okay, I cannot speak that much to it. I can speculate from my own experience and interactions, but I cannot. I just don't have the knowledge about how difficult it is.
Just curious.
But yeah, I think there's definitely some learning curve. And as far as I know, not all types of surgeries are equally kind of used with a robot. I think, as far as I know, urology is actually quite a lot of things are done with a robot. But there are types of surgeries that apparently like it's very uncommon to even use the robot. So there's difference in that. But yeah, right. So coming to the feedback. Yeah, so we had some examples how it looks like. It's like a 10-second clip of what's the context of which feedback is delivered, and you can see that it is kind of highly multimodal. You have a video recording that has like instruments and anatomic context, but you also have verbal speech that actually tells you, what exactly we should improve, or sometimes it's not that exact. So, and then there's the non-verbal components in terms of sometimes the surgeon communicates urgency to doing something. Specifically, there are things like addressing bleeding, it requires urgency, and there are non-verbal ways to communicate it, and there are, of course, emotional components, especially context like giving praise, things like this. Like surgeons are humans, they can get frustrated. Yeah, in terms of the data, from the point of view of like deep learning and the dimensionality of the data, there's not a lot of data. You have like around 4,000 lines of feedback, and the feedback could be line like that, but sometimes it's even one word, like okay or good. Sometimes it's longer. I will show some examples. And this collected already from 31 individual surgical cases. And then there are 4 different surgeons and 11 different trainees. So basically they're recipients of feedback. And the resident and fellow, the difference is that they're basically their experience level. The fellows are usually more experienced. Okay. Right, so from a technical perspective, the task is kind of multimodal fusion. You have the data from video, the data from audio, transcribed text, and then you want to combine these modalities, knowing that they are important, the context is important, interaction with these modalities. You want to combine them to be able to essentially extract categories of feedback. And they are not mutually exclusive. So as I mentioned, it could be anatomic and technical at the same time. It's more about the properties of feedback. It's like a multi-label setting. And in this, again, actually to give you these concrete examples I mentioned, so you have this anatomic, procedural, technical. If you look at these things to notice here, that you have this video, audio, dialogue, but you also notice that there's a kind of a dialogue and exchanges between, sometimes between trainee and trainer. So what you see in blue is actually what is annotated as feedback phrase. So that's one thing that's embedded in this. Another important thing is, as you see in this praise, as I mentioned, sometimes it could be just one word that tells you're doing good, and there's like an explicit affirmation that you're doing the correct job. But sometimes it can be much more elaborate and could be longer paragraph. And the third thing to notice is that normally when you have, and what, for example, GPT-4 is capable of doing to some extent, you can, for example, treat this task as a kind of a captioning task, in where you have a video or an image and you describe what's in the image with text, right? And you have the model thing. But the feedback is quite different in the sense that what you see, what the surgeon talks about is not describing what is being seen. It's not merely a description of like, oh, you see here the bladder or something. That's not the case. It's more about what you should be doing next where you are. So it's not necessarily aligned in the sense that the text is merely a representation of the image, just in different modality. That's not the case here. Right. So if this, but still, if you treat this as a multimodal fusion, there are approaches to multimodal fusion. And generally the approaches are to have models extract and process different modalities and combine information in kind of late fusion process. There are different types of fusion, but with limited data, it's usually late fusion is by the way, yes.
I have a quick question. Is the text basically just a transcript of the audio, or is this a different kind of text?
It is kind of a transcript of the audio. So you have two versions of text. One was manually transcribed. The other one was automatically transcribed. And we kind of, in the paper, compare this, how well we can transcribe it. The difference with the manual thing is that it's not transcribed all of it. It's not exhaustive transcription. It's just transcription of the parts that were considered feedback. Versus when you translate it automatically, you just take a window, right? And you don't necessarily know which part is considered feedback. There will be like a whole exchange plus multiple speakers. So it becomes a more complex thing, but yeah.
So the video is just going to be a collection of frames, right? Not the actual videos.
It is an actual video, but you're right in the sense when you put it in the model,
right?
You basically, it depends what model you use. We used, I'll talk a bit about this. We used a video mass autoencoder, which essentially extracts a set of frames from it and combines them, and basically that's you treat it kind of frames. Yeah.
So how would you match the frames to the transcribed text? Do you have like timestamps in the text?
Yes. So there are timestamps. There is some, as I mentioned before, that there's no guarantee of alignment. Like for example, even the visual context that started feedback might not necessarily be exact moment where the feedback actually starts, because you've seen something, it's something that triggered you to do it, and the feedback can happen after 5 seconds. This is actually still like work in progress. So it's not as easy, like, for example, just to train a representation that is aligned in embedding space, like at the meaning space, that you can just align it. There's no guarantee that it's going to be aligned. But in terms of the data format, yes, it's we have timestamps. We have basically video with audio recording, and they are aligned temporally.
Gotcha.
So yeah. So yeah, there are these classic approaches for late fusion, which essentially combines information from different modalities, and you can vary it. And actually, that's what we compare to. Like you can vary it in terms of complexity. How complex is the part that combines information? And the simplest one is, of course, doing simple voting. Right? You just have different modalities vote, and if all the information that you need to make classifications contained in just one modality, that could work pretty well. But if you have to somehow learn something between modalities, then it's more difficult. You can add more trainable components, and the more trainable aspects you add, the more complex relations you can learn. But at the same time, if you have data, then it's less likely you're going to learn this because you don't have enough data to learn very complex architectures. But we kind of looked at this variability of this. And the approach we proposed, and it was pretty effective, it was actually looking less at the architecture of the models, looking more at the training process. And the intuition here is that two things have to happen on a high level. First of all, there are not yet well specialized models for this kind of surgical task. They're medical models, they're not for surgery specifically. And there are two things that happen here. The first kind of task when we decompose in is having the models adapt their behavior to the surgical context, so become specialized in the surgical data. So that's the first part. And the second part is, once you have these models for different modalities specialized in surgical data, how can you learn how to combine this effectively so you get a gain? So that's the intuition behind kind of our stage training process we introduced.
Do you use there's various different like medical BERT or whatever?
Yes. So we looked, okay, I'll go into this. We looked at, we looked at BERT and with the medical BERT, there's a bioclinical BERT, and I think there are new ones right now. We're a bit surprised there was no gain from the medical BERT, but the reason is we have some intuition around it. If you look at this feedback that we have, it has some specialized terms, but not that many. It's actually a lot of kind of conversation, somewhat like a chat, and occasionally there are things like vena cava or like some anatomic things, but they are rare enough that it didn't help that much with the like a bioclinical BERT. Usually these clinical BERT models are trained on PubMed publications. There's a lot of jargon because it comes from medical publications, but this is not the case here. You don't have that much jargon. It's closer to the regular conversation with occasional terms. So we didn't get much gain from this. That makes sense.
Yeah, great intuition.
Okay, so yeah, so this first stage is essentially we used a model that's already trained on video, but of course these are not medical surgical videos. So we used a mascot encoder, which is essentially one of the transformer models for videos. And the problem is, of course, these models are pre-trained on like human activities, and they are not necessarily they're not specialized for surgery, and the first stage is trying to specialize them for surgery, but still it's useful with limited data because the model still learns how the image looks like. It already knows that, what are the edges, what are the objects, to some extent what the shapes are, and how the movement is modeled, right? But you still need to specialize to how the movement in surgery looks like. That's like a complex task, essentially overcoming the domain gap. And that happens across all these modalities in the first stage. And then the second stage, once we have these specialized versions for the surgery, we want to learn this part that how to combine them, right? That's the second stage. And in this case, we can use any of these late fusion architectures. And we actually showed that this is less important than actually this stage training process. Okay, so in terms of the results, it's a classification task and it's a multi-label classification. So if you look at anatomic and binary, if it's anatomic or not, what you see here is on the y-axis, you have the AUC score, and we use the AUC because the data is imbalanced. So if you just, for example, the anatomic feedback, I think it's around 30% of it. So if you just apply accuracy and say nothing is anatomic, you're gonna get 70% accuracy, which would be quite misleading. So we used AUC for this, and the interpretation is that, kind of 50 or 0.5 would be nothing, like it's meaningless because the model is not able to categorize things, versus like 100 would be perfect. Right. So you see on the individual modalities that in this case, in the case of anatomic, that just using the text is actually pretty good. And the reason is because there are a lot of mentions of like bladder or anatomic components that the model can pick up on this. The video is harder. It's still with fine-tune it, but it's not a clean, right? It's not a clean image as general images, so it's sometimes difficult. Let me compare to simple voting, which does not work that well here. And also joint. The joint essentially means this late fusion architectures, but we have the standard training process. Yeah.
Keith has a question for you. Do you want to unmute yourself, Keith?
Sure, yeah. I was curious when I was looking at the different modalities, it would seem most like, as this shows, text was the most important to determine these different categories. And here it looks like the ROC for text is not significantly different than the staged version, although the error is or the error range is lower for the staged. How did you assess if your method was better than text?
Sorry, then text only?
Yes.
Oh, yeah. So in the paper, because the gains, okay, I will go a bit further. Yeah, the gains are dependent on different components, right? There are different percentage of gains, and we basically repeated the process 3 times with different splits, calculated standard deviations, and we did actually a statistical test to see if it's significantly different, because there is some variability, right? When you do it on different data splits.
Thank you.
Yeah, so in this case, you can see there's a gain of around like 5.5% for the, for our stage fusion, which is essentially the green bar. And the AUC is actually relatively good for this. The other, I think the important thing from the also clinician's perspective and intuition behind it, if you look at the visual aid component, the intuition is also when you look at the data, and that's what's the expectation from the surgeons, that this is essentially a property of feedback when the surgeon was using something to point at things in the visual field. And the pointing is sometimes there's a laser that the surgeon can point, but they can also use the instruments like the tube for sucking blood. When it's bleeding, it can also be used for pointing. So you'd expect the video would perform really well in this, because there's this clear visual aspect that is important. So you see indeed here that, like, if you look at the visuality, and video is much more predictive than just this, for example, in anatomic. Text is still very useful because they are pointing words like here, there, look, that the model can still pick up on, but the video is also very important, which was kind of intuitive of what you should expect. And similarly for the praise is text is really good because essentially this is a variation, like a sentiment classification. Like the praise would have words like "you're doing good," "yeah," "nice," "continue." But we also would expect that video would be essentially meaningless here, because you can give, the way it's coded, the praise can be given for anything you do. So it could be a praise because you handled bleeding well. It could be praise because you identified the anatomic component well. It could be praise because you did the stitching correctly. So, it can happen in any visual context. So intuitively, you wouldn't expect video to give you much. And indeed, it does not. But there's some intuitions behind which modalities are important. Yeah, so with this, we kind of that's kind of the first step, right? There's a lot to go, and we essentially we try to automatically categorize things that are already happening in the surgical room, and we can use it, as I highlighted a bit, for trainer support. Like we can provide an analysis of what kind of feedback is important, what's the contents of the feedback that happens in live surgeries. And we're working towards kind of holistic analysis of the operating room interactions. And finally, one of the things you can do is provide this kind of dashboard that I highlighted at the very beginning that allows surgeons to see how they deliver feedback, but also what are the aspects that they focus on. Should they focus on this? Very important. There's of course the side on the trainee, which is how can we help trainee to become better when we know about this? And there's of course the skill assessment, in a sense. If you see that there's more feedback delivered on a particular aspect for their particular trainee, you can hypothesize that, for example, this trainee is not very good with technical aspects, and it's something they should work on specifically. So we can also, that enables this. One other thing for the future work is, of course, every feedback is delivered because something happened that triggered the trainer to give feedback. So the interesting future directions is also, can we identify these triggers and can really give it the lead to a necessity for feedback. So this is the area of kind of supporting the trainee. And finally, feedback quantification improvements. The categorization we have, although it's developed with clinicians, it is clinically validated, it has significance in predicting behavior. The issue in some ways is very, it's very coarse, right? It's not very fine-grained, just anatomic, is very broad. So there are things we're actively working on, kind of using unsupervised techniques to try to develop some categorization that's more fine-grained and will be more actionable. So for example, we can separate, if you have technical feedback, whether it's a feedback about the way you suturing or the way you're cutting things or you're using retraction, things like this, which would be potentially more actionable and fine-grained. And of course, like ideally, down the line, long term, you would expect that there is an intuition, and we know that what expert delivers is might be not necessarily optimal. It's still like a teaching, learner-teacher environment, right? So they use their best judgment, but they don't necessarily know whether this is optimal. And it is interesting in the long term, can you anticipate, what was the behavioral outcome of feedback? Would there be other moments that you could have delivered feedback that you missed that could have been effective? Or maybe some feedback was unnecessarily because it didn't really lead to behavior change, but yeah. Okay, so now I gave you kind of a deeper dive into a project where we essentially applied some of the modern AI to try to address human-centered project in a kind of specialized domain, collaborating with practitioners. But I want to also talk about the big other area of my work, which is, okay, we're using these AI techniques, but we know they are imperfect in some ways. We know they encode, and it's like a big thing right now, right? There could be unfair, it could encode biases. Another part of my work is also enabling people to understand what are the limitations and capabilities of AI models. And that's what I want to talk about in the second part of my talk. So specifically in this area, I worked on end user explainability of AI. So systems that can shape expectations of users. For example, that they have correct anticipation of what the model can and cannot do and when it's going to fail. I worked a bit on communicating what a recommender system do and helping people understand why they are given certain recommendations. But the part I want to really dive in here is my latest work on the social bias in generative AI that I have done at Caltech. And in this case, my main motivation is kind of to empower non-AI experts, domain experts like social scientists or ethicists to be able to inspect some of the modern AI tools using my human-centered design knowledge. Okay, so this is the project called BiasTestGPT, which essentially what it tries to accomplish. We try to empower domain experts to kind of test what limitations of modern AI, which is related to social bias. So this in the area of language models, but essentially, like for example, the BERT model that I showed was used for analyzing text in the surgery. So, but here you're focusing here on the language models, and the language models are that's all the hype right now, and they are trained essentially on kind of minimally curated data from the internet, like the Wikipedia data. You can argue has a bit higher quality, but there's like common crawl data, and this is actually not an easy task to even equalize or check all the data. And the whole advantage of the language models is they can leverage this data at scale without having to require human label. Right, so the common task when the language models are learned is the kind of self-supervised task when you essentially see, for example, in the sentence like Paris is the something of France, right? The model seeing for example, a text in Wikipedia knows what the correct answer is. It knows the capital would go there, so it tries to adjust its probabilities so it makes the correct guesses to what's the correct word there, and you don't need any labeling here. You just learn from the existing text. And similarly, the autoregressive models, the models that generate text, can find the continuations that are more probable. Right, that's usually the main underlying tasks for training pretty much all of the language models. But while it's very powerful, and with this kind of simple things, you can learn really interesting capabilities. There are also problems with it. And one of the problems is kind of stereotyping that the models encode. So, for example, you will see that in the contents that the model is fed, it may learn that he or she, like different genders, are more likely to appear in the presence of different professions. So, you more likely have articles or posts from people with, for example, males talking about engineering jobs than females, and then the model learns this kind of associations. Similarly, it could be much more nuanced. It could even associate certain names that are indicative of particular ethnic background with some kind of stereotypes about behavior. And this is a problem in many ways because when models generate text, they have a tendency to generate text with particular inclination. It can also translate to later using the models for classification. So our work here is, the goal is to create kind of a suite of tools that enable on-the-fly testing of stereotypes in language models. And specifically, the thing we want to accomplish is to empower domain experts and end users to be able to do it easily. There's a lot of this work done by AI experts, and there are a lot of methods people develop, but this not necessarily translates to arguably people that are most knowledgeable about issues of bias and the social interpretation of it. So we're trying to bridge this gap. And then save these discoveries to kind of structured data set that actually help engineers potentially test and fix the models. Okay, so the contributions of this work is we provide this open source, user-friendly social bias testing in language models. We have a framework for then we use generative AI to create data sets at scale, and we'll dive into this more. And then the broader impact is, of course, we want to empower end users who want to lower the testing effort. And also with user studies, we've shown that the tools we developed are high in usability and kind of increase awareness. Okay, so here's our framework on a high level. So we have the domain experts, the experts in ethicists or social scientists. We have an end user interface, a tool that allows to essentially use as a generator model to support generating diverse data set for testing different language models. So here we have these two big components, which is the user-centered part, and there's the technical part on the framework. And I'm actually hoping I can wait. Sorry, I have a live tool that I wanted to show you, which maybe I can do, but I didn't start it earlier. So. Sorry about that. Okay. Let me go further, and when it starts, I will show this to you. Okay. Right. So we created an end user bias testing tool that's essentially shared on a popular platform, AI platform called Hugging Face. So that's basically a platform where there are a lot of models, data sets, and spaces that you can test models. And that kind of enables general public to use this tool. We open sourced it. And I wanted to show you how it looks like. Okay. Yeah, it's a thing with the live tools. Let me go back to this, and I will give you a bit of a technical side on this. So, our framework is essentially the idea is if you have a bias, a stereotype that you want to test, essentially the stereotype is defined as kind of different behavior of the model that is problematic for different social groups. So social groups could be, in this case, genders, for example, male, female, and you can describe social groups in a flexible way with terms. So it could be like what you see, descriptions like this, but you could describe, for example, names that are specific to particular ethnicities or any other flexible description that captures different social groups. And then you have attributes. In this case, there will be the difference. You're testing the difference between a model tendency to associate male with science and terms related to science versus, for example, poetry for women. And that's kind of the specification of testing stereotype. And what you want to test is whether the model has a tendency to associate certain attributes with different social groups. So So our framework involves, when you have this kind of specification, you can flexibly define it as a domain expert. And we ask the model, a generator model, to basically generate a set of sentences that mention this social group and the attribute in the same context. So it creates, basically, it creates a realistic text describing how these social groups and attributes are mentioned together. And with this, we have a kind of sentences that, for example, have something like, he's very good at science, my daughter writes poetry. And these are very simple examples, but I give a more complex examples when you see the more naturalistic sentences, like a male math teacher explain the concept of algebra to the students. Right, so you have these sentences when you have these associations. And the thing is, now you want to make a counterfactual, an alternative, when the only thing that changes is the, in this case, the profession stays the same, but the only thing that changes is now it's talking about, for example, female. So then we do this additional prompting where we ask the model to rewrite the sentence, just swapping one social group for the other, keeping everything the same. And the importance of this is that our sentences, compared to prior work that used, for example, simple templates, I will show it a bit, but the simple template, you can do something is something, but that's not very, like, he is a teacher, right? That's a very simplistic sentence. That's not very natural. But if you have naturalistic sentences, you have this longer references in the text that also relate to social group. So basically doing this, this prompting and doing alternative pairs allows us to keep track of kind of all the co-references in the sentence for the particular social group. Okay, what we end up with is a set of like thousands of actually different contextual sentences where we have paired alternatives with he's very good at science, she's very good at science. The only thing that changes is the social group. And having this, we can actually test an other language model in terms of, given this pair of he, she, which one is more probable, like which one the model thinks fits more in the data it has learned. And the probable is essentially, the model captures, based on the language it has learned, how likely different sequences are, right? And you can leverage this information to see what the model thinks, which version is more likely, and it also translates to how likely is models to generate this particular version. So that's the bias quantification. And basically, this is called the intra-sentence metric, when you look at kind of differences within the association within the sentence. Okay, maybe to start this, I can show you. Okay, right. So I showed you the technical part of it, but we have the important part we wanted to do is to have this user-centered tool that allows non-expert to do this, right? Like social scientists or ethicists not necessarily gonna run a code to test language model extract probabilities. So that was the idea for this. And this tool is hosted on Hugging Face, so it's public. And the thing what you have here is you have predefined biases. So there are biases that are described in literature, like the gender profession I talk about is very well documented, but there are other ones that are related to intersectional biases. So when you select this, the tool automatically, oops, the live tool. Let's try it again. There's something on the internet. Okay. Well, okay, then I will go to the slides. I don't know, it was working well, but that's the caveat of live tools and presentation. Although it's hosted on we're not even hosting on our servers, but okay. Anyways, I can show you. Let me go back to it. Right. So. So in general, yeah, you can put the sentences, you can describe, the attributes you want to test, and basically you can test the model and see, you get a kind of score. Given all this, there are thousands of sentences, how likely is choosing the stereotype version that is defined by the experts. So what is considered stereotype is essentially what a domain expert would define. And the score will give you, for example, 61 means that in 61% of this paired, paired choices, it shows the stereotype version. Like 50 would mean that it's unbiased in a way that it's equally likely chooses stereotype and the stereotype version. And then we have this breakdown for different attributes. So for example, you have these attributes here for intersectional bias, like curvy, feisty, and you can see per attribute that the attribute of curvy is actually in 65% of the cases is more associated with the first social group. So in this case, there are names associated commonly with African American female. Yes. And then on the other side, you see, for example, that intelligent is the model really associates this with the names that are associated with like Caucasian males. So essentially, there are multiple ways. Yeah, and the tool enables this and doing it on the fly. Right. Okay. Any questions about this? Because I kind of yes.
Can you go back to that last slide?
Yeah.
So when you're calculating the probability of, these two sentences with these two different demographic groups, like I found using that metric that, sometimes like, yes, it prefers like men over women for this like sentence, but the probabilities are still like really close to each other. So it's like hard to parse how significant it is. Do you have any thoughts on kind of like how to think about that, especially in the context of this framework?
Right. So we did tests on the variations. So the usual problem of this is that you can look at the probabilities, but the models are not necessarily well calibrated. So the probability doesn't necessarily reflect like meaningful. It's not really a probability. It's like it's squashed into probability. Okay. But it still gives you like what the model. Ultimately, the model will choose one version, and it will choose the version that's basically the probability we extract is the loss that is used also in the training of the model. So that's basically what the model will extract. Now, having said so, the models are kind of brittle in the sense that if you change some things in the text, the things might change quite a lot. That's why it's important to kind of test across thousands of sentences, not just in one context, to be able to see how the variations, how much they affect and whether they're systematic. So if you test just one thing, you can sometimes do a simple thing like add, D or A, and it's going to change things. So that's why it's kind of important. So that's my view on this. I think that generally that you want to have variations, and that's what our method kind of enables, is that we generate the sentences at scale. We have like thousands of sentences, and you average it out across the things, and you look at the standard deviations as well. So if that makes sense. Actually, this will probably be easier to see when I go here. Okay, let me go through this quickly over time. Yeah, so we actually looked at these are our generations and the manual templates, which is considered kind of a very controlled setup. As I said, it has limitations because it doesn't represent a real text, but you really know what is there. And what you see here, there are a set of biases around gender, around intersectional and emergent stereotypes. And these are actually informed by prior work. And we have a set of biases we also kind of found through the use of the tool. And then we have different language models. So you're probably familiar with BERT, GPT-2 family models, are kind of older models, but we also can test more modern things like Llama, 3 billion, 7 billion, and some of the specialized like biomedical models, like the BioGPT. And what you see here is the score, stereotype score, which is the higher is the more, more stereotype choices it makes. And of course, 50 would be completely unbiased. And now, okay, I'll give you this scoring across models and across biases. And things to highlight here. First, if you look at the gender biases, what it tells you, if you look at the model, like I think the GPT-2 model, 75 means in 75% of this paired choices, it will choose the stereotyped version. So it is quite biased. And it's not that surprising, it's actually well documented. We show here that using manual simple templates, it's actually not necessarily going to reveal these things. And it's better to have naturalistic sentences. At least they are representing the context of actual generation that the model will create much better than kind of handcrafted sentences. So we show this in the gender that we are more sensitive to detecting some of the biases. And similarly in the intersectional biases, when we have both gender and race together, these biases are generally considered more challenging because because of the fact that there's less data that mentions all this. So the model is kind of undertrained in this particular, when you have this intersectional part. So we also see that we can detect things a bit better than manual templates. The underlying thing is, of course, that bias is kind of subjective. In a way, you can argue, what is the bias? But I think I want to show you why do we have different scores, and what drives these differences between the simple templates and our generations. So here's an example of the differences. For example, in this case, when you have physics, so like a technical field associated with gender, the simple template is actually how it has been used in a lot of prior work. You have brother likes physics or sister likes physics, right? Which version is more probable? In the sense the model, you would think it doesn't choose the stereotype when you test something like this. And sometimes these templates are not necessarily grammatical, like the second one is brother like physics, it's nothing fully grammatical, but you would conclude, okay, there's no problem, or maybe it's anti-stereotyped in a way. But then if you look at some of the generations that we had in our models, you can see these are generations of physics, and the model, they all use physics, but it's in the context of college education, which is a sub-context of it that is probably more likely to be used in practice. It's more likely what the model will use. And you can see in this particular sub-context that we can discover with generations, it is actually stereotyped. So the conclusion could be quite different depending on what context you use. That makes sense. Okay, yeah, so we did the user study to actually see, well, the tool didn't work right now, but it does work. And we did a user study when we had participants from social sciences, psychology, and liberal arts, so people that didn't even sometimes know what is BERT as a model. And we asked them to interact with this tool, and we measured usability and kind of their change in awareness of bias and interest in kind of being able to test bias in AI or any other issues. We had a study when we asked them to use these predefined biases I showed, and also create their own custom biases, so they could enter terms and generate their own sentences to test things on the fly. And we showed that first, the usability of the tool is quite high. It was relatively easy to understand for people how to get to test the model and then use the tool. We also found interesting aspect that they indicated interest in the ability to test bias, and they're willing to some extent to spend their own time to be able to test bias, especially in the models they use. So there is a public kind of interest in understanding these issues. At the same time, we also looked at whether after using the tool, they change their awareness of bias. So yeah, and we found that there are significant differences in their they felt that they know about fairness considerations much more, and they also felt that they understand better how the AI can propagate biases in the way it is used. We also did an interview, and the positives were, as I mentioned, the tool was kind of easy. The bias score was quite intuitive. There are a lot of bias scores. Some of them are quite difficult to interpret. This is considered quite intuitive, and the detailed breakdowns were also very useful for giving them a deeper understanding. But there's an interesting finding related to some of the challenges, especially in the custom bias setting, when they can write what they think they would want to test or what they expect the model may be biased on. They felt a bit of an unease of expressing these biases because they thought this is something that they express as they think this is a bias and this is a stereotype, although it was just for testing the model. So this is a kind of interesting HCI finding on engaging general public into testing such models. So yeah, the future directions here is about engaging more the domain experts, expanding the tools to multimodal models. Right, there's a lot of work on multimodality. And also we can test the models in different contexts. As I mentioned, we have an ability to generate data sets at scale. And it's interesting if different style of conversations have different kind of bias injected into the models. So like book or social media conversations. And finally, of course, building the biasing, which we have started some of the work on this as well. Okay, so if this kind of zooming out, these are the two areas I talked about. And my general goal is essentially, I want to develop systems, interventions, and design principles that are, that make use of AI effective, inclusive, and safe. And to accomplish that, the effectiveness, what I believe is there's several principles I've learned that are useful to follow. first of all, for effectiveness, aligning with current human practices. If you collaborate and the AI is supposed to assist people, it's very important that the outcomes and the tasks you tackle are not purely technical for its being interesting on the technical side, but also have, for example, in this case, clinical relevance and being actionable, and having a plan of how it's going to be actionable. And there's also, I think, interesting AI assistance, but not necessarily trying to replace humans. And I think there's a lot of value in that. In the inclusivity space, there is, I think it's very important to design with users and experts when you create such models and you use them and interpret their behavior. Because AI becomes complex and now it gets narrow, like only experts understand some of the nuanced aspect of it, it's important to kind of have an adaptive level of detail for inspecting AI, and that's the tool we created was kind of an attempt to do this. And there's interesting things in kind of changing behavior, like we can, the generative capabilities that we use for testing bias can also be used for tailoring content, for things like training, education, or behavior change. And finally, the safety, as I showed, the tools for social bias testing, hallucination testing are very important, and that's actively what I'm engaging in. And the one aspect I mentioned is I think that it's important to incentivize contributions from non-AI experts to contribute to improving AI safety. So engaging again, social scientists, ethicists, doctors in providing feedback on AI. And there is a barrier because it becomes complex, it moves fast, and you feel kind of excluded. Okay, with this, I would like to thank all my mentors, Gary Shea, who was my PhD mentor, Anima and Kumar, who's my postdoc mentor at Caltech, and collaborators from health domain, and my mentees that I had the privilege to kind of guide over my time at UW at Caltech. Yeah, thank you so much, and yeah, happy to take questions. Yeah.
I think it was really cool how you showed the auto bias or bias tests to people to like see how that informed the way they think about bias. Can you talk a little bit about your vision on how the tool would be used from like modelers or engineers to like improve their systems?
Right. So the tool, so the finished the vision we have for this, and show is kind of usable for non-expert. The idea is like to bridge the gap between the people that I think are equipped to bias is essentially a social issue. It's an evolving and interpretative issue. I don't think AI engineers are the most equipped to do it, and they also understand it in some ways. They want to be very careful. They don't want to define what the bias is. They want to have a paper, a data set already tells them. So the way I see that the tool can bring it is that you will have a domain expert being able to define what they find problematic, right? What are the biases that they believe are problematic? And then the tool, what it does when it generates data sets, it actually saves them in a structured format as a data set that you can actually use as an engineer to test bias in model or use for debiasing. So it's very much a bridge, like having domain experts being able to define problematic biases and then translate this to structured data for engineers to be able to technically, address this. If that makes sense. Sorry.
I'm so sorry. I have another meeting, but we have a one-on-one. Great talk.
Thank you. Yeah. Sorry.
Thank you. I really enjoyed your presentation. Following up on this question,
yes.
I don't know too much about this. How many of these stereotypes carry on between sentences? Because I can imagine the naturalistic sentences you had here. My template studied physics my doctor studied physics at college, and he was tall and whatever in the next sentence.
Right.
I can imagine it, AI engineers, whatever, you red team out the sentence level templating, but are there more pernicious ones that carry between sentences? How do you think about this?
So it is kind of interesting because it's a challenging area. Like what we show with this tool is like, it's possible you can make this pipeline, and then basically the type of bias we're testing is a particular type of bias in a particular task. It is a bit more complex area because you can have this biases between sentences. There are other types of biases than stereotyping. For example, stereotyping is essentially you have just an equal production or an equal representation between the social groups. But the other things are, for example, when the model doesn't know a particular social group at all, it doesn't represent it at all. That's I think it's called like othering, that you don't even have, the model doesn't even know about this. So it just completely cancels this whole group. And then it hallucinates. And it's even worse. So there are other types of problems. I think the other thing that is very got traction recently, because the simplistic definition of, the differences between social groups, there's a discussion, what differences are actually harmful or problematic? Because there will be differences. If your goal is to make no differences, for example, there are differences in terms of, and then, okay, you can get into discussions around it, but there could be like biological differences that are like immeasurable and the model can represent them. And that might be fine, but you can also argue that. So there's a bit of like a very careful considerations here. Not all the differences are problematic and not in all contexts. That's what I would say. So it's kind of important in the context you're gonna use the model. And I would even say from my collaboration with like humanities, social sciences, there are applications in which you actually want the model to express and capture biases. For example, you want the model to fit into conversation on social media about elections people work on. You actually want the model to model correctly what the underlying data is, because it allows you to explore these biases. So if you treat it as a research tool, as a model that fits the data and allows you to explore things, that's actually quite useful. You don't want to, like, for example, debias it. I don't know if you've heard about this high profile thing, I think from Gemini. If you try to debias things indiscriminately, like you can change historical facts, like the founding fathers, and they can be any race, which is like, okay, in the simplistic definition, you want the equal representation. That makes sense, but it shows you how far you can go in the direction is not correct. So that's why I think it's important to kind of engage this, domain expert and have this interpretative value. That's what I'm kind of trying to accomplish. But a lot of things in AI are really interested in creating, new metrics to measure things and basically using particular data sets and doing this. They kind of leave the messiness of social interpretation outside of it, trying to combine it in a way, but it is challenging. That makes sense. Yeah.
On the first area of work that you talked through, so you talked through some of the work that you're on now, where you're kind of extending the approaches for using this categorization that you've done and this validation you've done on the different types of feedback and different analysis modalities, using that to kind of help engineer approaches for getting towards better feedback. What's gonna change behavior, how to could you talk a little bit about how you're using the feedback? Like, do you have a feedback process in which you're using that to optimize behavior change? Or
so right now we're not explicitly doing it. Like right now, what this work does is we have categorization of meaningful categories. Like we come up with meaningful categories. We show that we can detect them automatically from the data. We show they're statistically associated with behavior. We actually, the next step we're also doing, we see that they're in some ways too high level for some kind of actionable things at the moment. So we're trying to refine this categorization further. Down the line, so to answer your question, right now this is an analysis of what is happening in real context with experts. So it's more retroactive. Having said so, we have done, and there are published studies that I can also share, that we did targeted experiments with feedback. So we did experiment when they had a task. We gave them, we defined like 8 pre-recorded feedback categories that were triggered, and we checked whether this reduces their error rates. When they do the task with, after feedback, and we compare it to the group. And it was like purely experimental controlled study, not with patients, but with kind of props. Then you have simpler tasks, right, that they practice on. And we do show that that was kind of part of this user-centered approach. Like you want to prototype whether it's worth putting effort in the automated system. Will it change things? Like how would you use it for benefit? And we did studies when we did kind of on the technical side, kind of primitive studies, because they're just purely manual controlled studies. But with this, we found out that, having the capability to deliver feedback live, like real time or even post task is actually useful. It will improve their performance. So there are studies on this, but right now these are not fully connected. We don't have like end-to-end system that goes through, automate things, delivering things, and then working with it. So, but that's probability one. And I think there are high level, like two different tasks, like, you may want to automate surgery completely. That there are a lot of problems with. But I think what we also want to do, like, first thing is just automate guidance, like assistance, right? Can you help guide? Because it's also expensive. It requires, like, even recording surgery for training tasks requires the expert to spend time instead of doing surgeries and looking through what the trainee did, right? And guiding this on non-real surgeries, like the simple task. So the point is we are attacking the problem from two sides. We do prototypes and controlled experiments. At the same time, we look at historical things and patterns in this. And at some point, I think we'll combine both.
All right, thanks everyone.